Hello everyone, welcome to the first part of tutorial 4. So let's start with question number 1a. In this question you are given two equivalence relations on a non-empty set X. Okay, I stress they are on non-empty set X, and you are asked to prove or disprove whether the union of R1 and R2 is an equivalence relation or not. So it turns out that the union of two equivalence relations need not be an equivalence relation, and this is demonstrated by this counter example. So I consider my set X consisting of elements A, B, C, and let me have equivalence relations R1 and R2. Okay, so R1 has the elements A comma A, B comma B, C comma C, A comma B, B comma A, and R2 has the elements A comma A, B comma B, C comma C, B comma C, C comma B. It's easy to see that both of them are equivalence relations over the set X. They are reflexive. Each of them is a reflexive relation, symmetric relation, and a transitive relation. I'm not going through that. It's easy to verify that. Now, if you take the union of these two relations R1 and R2, you will have these ordered pairs, and it's easy to verify that R1 union R2 is a reflexive relation over the set X because you have A comma A, B comma B, C comma C present in the relation. The union is also symmetric because if you have any ordered pair of the form A comma B in the union present, and the ordered pair B comma A is also present in the union. But it's easy to see that the union here is not a transitive relation. Specifically, you have an ordered pair A comma B and an ordered pair B comma C present in R1 union R2, but A comma C is not present in the union, and hence the transitivity property is violated. So in general, the union of two equivalence relations need not be transitive. We can prove that it will be always reflexive and symmetric. If I take the union, it will be always reflexive and symmetric, but the union need not be a transitive relation. In part B of question 1, we are supposed to prove whether the we are asked to prove or disprove whether the intersection is an equivalence relation or not. And it turns out that the intersection of two equivalence relations over the same set X is always an equivalence relation. So let's prove the three required properties. So if I take R1 and R2 to be equivalence relations over the set X, then since R1 and R2 are individually reflexive relations, you will have ordered pair of the form A comma A present in both R1 as well as in R2. And as a result, you will have ordered pairs of the form A comma A present in the intersection of R1 and R2 as well. That shows that your intersection of R1 and R2 is a reflexive relation. Now let's try to prove the symmetric property for R1 intersection R2. So for that, I consider an arbitrary ordered pair A comma B to be present in the intersection of R1 and R2. Since it is present in the intersection, as per the definition of intersection, it will be present in both R1 as well as R2. Now it is given that my relation R1 and relation R2 are equivalence relations. So individually both of them are symmetric relations, and as a result of that, the ordered pair B comma A will be present in R1 as well as the ordered pair B comma A also will be present in R2. So since B comma A is present in both R1 as well as in R2, it will be present in their intersection as well, and which shows that the intersection will be a symmetric relation. Now consider the transitivity property, for which I consider arbitrary ordered pairs A comma B and B comma C to be present in the intersection of R1 and R2. So since it is present in the intersection of R1 and R2, the two ordered pairs will be individually present in both R1 as well as in R2. And since R1 and R2 are individually equivalence relations, each of them satisfies the transitivity property, due to which I get that the ordered pair A comma C is present in both R1 as well as in R2, and hence the ordered pair A comma C will be present in their intersection as well. So now you can see that the argument that we have given here for the intersection of R1 and R2 to be a transitive relation need not hold for the union. And this is precisely the reason due to which the union of two equivalence relations need not be a transitive relation and hence an equivalence relation. You can verify that. Now in question number 2, again you are given two equivalence relations over a non-empty set, and we want to prove that the union of R1 and R2 will be an equivalence relation if and only if the composition of R1 and R2 is equal to the union of R1 and R2. And this is an if and only if statement. Okay, so we have to give two proofs. We have to prove the implication in both the directions. So let's first prove the implication in the direction where I assume that the composition of R1 and R2 is equal to their union. Under that assumption, I will be showing that R1 union R2 is an equivalence relation. And I will be just focusing on proving that the union of R1 and R2 is a transitive relation, because we can always show that the union of R1 and R2 will satisfy the reflexive property and symmetric property. It's only the transitive property which is missing. And what we will show is that if this premise holds, then the union of R1 and R2 will satisfy the transitivity property. So let's consider arbitrary ordered pairs A, B and B, C to be present in the union of R1 and R2. Now, because of the union, there could be three possible cases depending upon where exactly the ordered pair AB and ordered pair BC belongs. So case 1 could be that the ordered pairs AB as well as BC are present in one of these two relations, at least in one of these two relations. Say in the relation Ri, where Ri could be either R1 or R2. If that's the case, then since that relation Ri where both AB and BC are present is also an equivalence relation, mind it, we are given that individually, we are given that both R1 as well as R2 are equivalence relations. So if both AB and BC are present in the relation Ri, then as per the transitivity property, the ordered pair AC will be present in Ri as well, and hence it will be present in the union of R1 and R2. Case 2 could be where the ordered pair AB belongs to R2 and the ordered pair BC belongs to R1. Right? In that case, you will have A, B, B, C present in the union as well. Now, if that's the case, then as per the definition of composition of two relations, the ordered pair A, C will be present in the composition of R1 and R2, because you have an intermediate B. So AB is in R2 and BC is in R1, so hence AC will be in R1 composition R2. But our premise says that the composition of R1 and R2 is exactly the same as the union, right? So if A, C is present in the composition of R1 and R2, it will be present in their union as well, and hence in this case also we proved the transitivity property. The tricky case is when you have the ordered pair AB in R1 and the ordered pair BC in R2. In that case, I can't apply the same argument as I applied in case 2. So I have to do something extra here. So what I do here is I apply the symmetric property for the relation R1. So remind it, R1 is an equivalence relation and hence it has the symmetric property. So since AB is in R1, we will have B, A in R1. Due to the same reason, since R2 is also satisfying the symmetric property, we will have C, B in R2. And as a result, I can say that the ordered pair C, A is present in the composition. But now, that's not my goal. My goal is to show that A, C is present in the composition, and then I can use the fact that the composition of R1 and R2 is same as the union and conclude that AC is in the union as well. So what I do here is, since I know the premise says that the composition of R1 and R2 is same as their union, I can conclude that the ordered pair C, A is present in the union as well. Now, if it is present in the union of R1 and R2, it will be present in at least one of these two relations, either in R1 or in R2. So without loss of generality, let it be present in R1, right? What does this without? So this WLOG here means without loss of generality. So uh, whatever argument I am going to give, assuming that C comma A is present in R1, can be applied in also symmetrically for the case when C comma A is present in R2. Okay, so assuming C comma A is in R1, since R1 is also symmetric, we get A comma C also present in R1, and hence A comma C will be present in the union of R1 and R2, right? So we have proved the implication in this direction. Let's prove the implication in the other direction. So I am going to prove that if the union of R1 and R2 is an equivalence relation, then the composition of R1 and R2 is equal to their union. So I have to prove the equality of two sets. So I have to prove that R1 composition R2 is a subset of their union, and I have to prove that their union is a subset of the composition of R1 and R2. Then only I can conclude that these two sets are equal. So let's prove that the composition of R1 and R2 is a subset of their union. And how do I prove that a set X is a subset of set Y? I have to show that you take any element from the set X, it will be present in the set Y as well. So that's why I am taking an arbitrary ordered pair A comma C present in the composition of R1 and R2. So since it is present in the composition of R1 and R2, what I can say here is that as per the definition of composition, there should exist some intermediate element B such that A comma B will be present in R2 and B comma C will be present in R1. Okay, that's a definition of composition, and that means that the ordered pair AB is present in the union of R1 and R2, and BC is also present in the union of R1 and R2. And since I am assuming here that R1 union R2 is an equivalence relation, that is the premise, it will be transitive as well. And if AB and BC are present in the union and it is transitive, that means AC is present in the union as well. So what we have shown here is now you take any element, any ordered pair AC in the composition of R1 and R2, it will be present in the union of R1 and R2 as well. Let's prove now Y is a subset of X. Namely, we will prove that the union of R1 and R2 is a subset of the composition of R1 and R2. So again, let's take an arbitrary element, namely an ordered pair, arbitrary ordered pair AB present in the union of R1 and R2. We will show it is present in the composition of R1 and R2. Again, there could be two cases depending upon whether AB is in R1 or whether AB is in R2. So again, without loss of generality, assume that it is present in the first relation. And I know that my relation R2 is reflexive, and I am assuming here that the relations are over a non-empty set. That means my set X has at least one element A. So since my relation R2 is reflexive, I will also have element ordered pair A comma A in my relation R2. And now I can use the definition of composition of R1 and R2. I have A comma A present in R2 and I have A comma B present in R1. So I can say A comma B is present in the composition of R1 and R2. Okay, so that shows that Y is also a subset of X, and hence the two sets are equal. In question number 3, we are defining a function P of n which denotes the number of equivalence relations over a set S consisting of n elements. Okay, so P of 1 means number of possible equivalence relations over a set consisting of one element. P of 2 will give you the number of equivalence relations over a set consisting of two elements, and so on. Now the questions ask you to either prove or disprove whether P of n satisfies this condition. So here the C function is the combinatorics function. Namely, it denotes here So C of n minus 1 comma j, here the notation denotes the number of ways selecting j objects, j distinct objects, or j objects we can say, from a collection of n minus 1 objects. That's the notation C of n minus 1 comma j. Okay, so basically this is a recurrence equation. What exactly we mean by a recurrence equation here? We are trying to express the value of the function p on input n in terms of the value of function p on previous input, namely on inputs of size less than n. Okay, so we are asked to either prove or disprove whether this condition holds or not. So in fact we will prove that this is true, this equation is true. So the first thing to observe here is that the function p of n also denotes the number of partitions of a set S consisting of n elements, because remember we have proved that every equivalence relation gives a partition and every partition corresponds to an equivalence relation. So the number of equivalence relations is nothing but the number of partitions over that set. So now we will focus our argument based on the fact that P of n denotes the number of partitions of a set S consisting of n elements. So imagine your S set S has n elements, and what we are going to do is we are going to discuss what are the various ways in which we could partition this set S. So for that I consider the first element A1. Now in order to partition the set S into various subsets, definitely the element A1 will be present in one of the subsets in that partition. Okay. And along with the element A1, there could be j other elements from the set S in the subset in which the element A1 is present. Now the j ranges from 0 to n minus 1. What does that mean? That either the element A1 might be the only element in the subset in its partition, that means when you are partitioning the set S into various subsets, A1 is the solitary element in the subset in which A1 is present. That's one case, in which case my j will be 0. Or my partition could be such that the A1 is present along with all other elements of the set S in its subset, in which case j can take the value n minus 1. So that's why the range of j here is from 0 to n minus 1. Okay, so that means what I am saying here is that irrespective of the way you partition the set S, the subset in which A1 is present, along with A1 you will have j other elements. So in total that subset will have j plus 1 elements, and the j elements will be chosen from the remaining elements A2 to An, right? So how many ways you can pick those j elements from the remaining n minus 1 elements? That's why the notation C of n minus 1 comma j is coming into picture here, right? It's not the case that only the first j elements outside A1 will be present along with A1. You can pick any j elements from the set A2 to An. That's why this expression C of n minus 1 comma j will be featuring here. Now once we have decided which j elements are going to come together with A1 in its subset, the remaining elements, which are now n minus j plus 1 in number, have to be partitioned, right? And there are these many number of ways of partitioning a smaller set consisting of n minus j plus 1 number of elements, right? That means once you have decided that, okay, I am defining a partition where along with A1 these other j elements are going to come. Once you have decided which j elements are going to take the position along with A1, now your remaining elements are n minus j plus 1. And now you have to worry about how you are going to partition that smaller subset. And now as per the definition of my p function, there are p of n minus j minus 1 number of ways of dividing that subset. So once you have decided which j elements to occupy, or which j elements to put along with A1. These will be the total number of ways in which you can partition the set S. So that gives you one type of partition. Okay. Now since j ranges from 0 to n minus 1, you have n number of such possible types of partitions. So that's why we get this overall formula. My first class of partition is where the element A1 is only the only element in its subset. Remaining n minus 1 elements are now partitioned into various subsets. So that's one category of partition. There are these many number of partitions of that type. My second category of partitioning of set S is where along with A1 I also put one additional element in that subset. That additional element will be chosen in these many number of ways, C of n minus 1 comma 1. And now the remaining n minus 2 elements are partitioned into P of n minus 2 number of ways. And continuing like that, my last category of partitioning is the following, where I put n minus 1 elements along with the element A1 in its subset. That means that whole set S is the only partition. Okay, in which case I have to now partition the remaining elements which are now 0 in number. So that's why P of 0 I can define to be 1. That means if your set has only, if your set is an empty set and there is only one way of partitioning it, namely no way, right? So I can define P of 0 to be 1, and now you can check that P of n satisfies this equation. Okay, and all these different types of partitioning are disjoint. There won't be any partitioning which will be present in which can be considered as two different types of partitioning, because the value of j is different for each category. Now in question number 4, we are supposed to find out the number of partial orderings over a set S consisting of 3 elements. Okay. So instead of enumerating all possible partial orderings over this set consisting of 3 elements, remember partial ordering means your relation is reflexive, antisymmetric and transitive. So instead of enumerating all such relations, what we will do is we will count a number of distinct Hasse diagrams which we can draw using these 3 sets, because remember each partial ordering can be represented by a Hasse diagram. Okay, so it turns out that we can draw 5 different categories of Hasse diagrams over this set, and let's consider each of them, and in each category we will count how many Hasse diagrams we can draw. The first category of Hasse diagram is where I have no edges among the nodes. So I have the nodes AI, AJ and AK, where AI can be any value in the set 1, 2, 3, AJ can be any value in the set 1, 2, 3 and AK is any value in the set 1, 2, 3. What exactly is the relation corresponding to this Hasse diagram? The relation here will be AI is related to AI, okay, AJ is related to AJ and AK is related to AK. Remember, in Hasse diagram, the directions are not there, self loops are always implicit, transitively implied edges are also there, and so on. So the relation corresponding to this Hasse diagram is this relation, which is a partial ordering. Now the question is, how many types of Hasse diagrams of this category I can draw? I can draw only one. I can draw only one Hasse diagram like this, because it doesn't matter whether AI is 1 or 2 or 3, right? The resultant partial ordering will be the same. Okay, so I can have only one partial ordering whose Hasse diagram will be of category A. My category B Hasse diagram will be like this, where I will have, so this is a relation, this corresponds to the relation where I have AI related to AI, AJ related to AJ, AK related to AK. Remember, self loops are always implicitly there, and we have the ordered pair AI related to AJ, right? Because the directions are always assumed to be from bottom to up. So the question is, how many partial orderings of this type we can have? And it turns out we can have 6 different partial ordering depending upon what is your value of AI and what is your value of AJ, because your AI could be either 1 or 2 or 3. If my AI is 1, then that is different from the case when my AI is 2 and so on. So you have 3 choices for the element AI, and once you have decided what's your AI, you have now 2 choices for AJ, because AJ has to be different from AI. And once you have decided AI and AJ, you don't have any other choice remaining for AK. The third element which is now left has to be AK. So that's why I can have only 6 possible partial orderings in this category. Okay. My category 3 could be where I have a total ordering among AI, AJ, AK. Namely, my Hasse diagram is a chain. And it turns out that we can have 6 partial orderings of this category depending upon what are my values of AI and AJ. So I have 3 choices for AI. My AI could be either 1, 2, 3. Once I have fixed AI, I have 2 choices for AJ. And once I have fixed AI and AJ, the third element will be my AK. So that's why I will have 3 different Hasse diagrams in this category. Fourth category is where you have a Hasse diagram where you have a least element and 2 maximal elements. In this category, we can have 3 partial orderings depending upon the choice of your least element. Your least element AI could be either 1 or 2 or 3. Once you have decided your AI, it doesn't matter whether what is your AJ and AK. They are going to be the remaining 2 elements. So you can have only 3 partial orderings of this category. And your last category is when you have only the greatest element, namely AK, and 2 minimal elements, AI, AJ. In this category, you can have 3 partial orderings depending upon what is your greatest element, the choice of your greatest element. The greatest element could be either 1 or 2 or 3. Once you have decided what's your greatest element, it doesn't matter whether AI is what are your remaining elements, AI, AJ. They are going to be the remaining 2 elements. Okay. So that's why if I now count all the different partial orderings under various categories, I get 19 different relations over the set 1, 2, 3, which will be reflexive, antisymmetric, and transitive. Okay. In question 5, you are given the following. You are given an arbitrary poset, and for any subset T of that set S, an element X from that set T will be called as a minimum element if that element X is related to all other elements Y of that subset T. Okay, so here I am defining minimum element with respect to the subsets here. It's not a global minimum element, it's defined with respect to a subset of the set S. Now, in the question, you are given the condition that your poset is such that every non-empty subset T of S has a minimum element. That means it doesn't matter what's the size of your subset T. You take any subset T of the set S, a minimum element as per this definition is bound to exist. So your poset is like that. Under that condition, you have to show that your poset is actually a total ordering. Okay, it's not a partial ordering, but it's actually a total ordering. So remember, the definition of total ordering is you take any pair of elements, they will be comparable. Either the first element is related to the second or the second is related to the first. You won't have incomparable elements. So that's what we are going to do here. We will take an arbitrary pair of elements A, B, which are distinct, and we will show they are comparable. That means either A is related to B or B is related to A. Remember, this less than notation does not mean the numerical less than notation. It means that A is related to B or B is related to A as per your relation less than equal to, where less than equal to is not a numeric less than equal to relation. It's an arbitrary relation which is reflexive, antisymmetric, and transitive. So how I am going to show that either A is related to B or B is related to A, I will take the subset T consisting of the elements A, B. And as per the given condition, this subset T also will have a minimum element. Okay. Let's denote that minimum element by X. Now, the definition also says that the minimum element will be within that subset itself. And my subset here is the set A, B. That means that minimum element can be either A or B. If the minimum element x is A, then we get that A is less than B as per the definition of the given minimum element. And my A and B are distinct. That means A is related to B and hence A and B are comparable. Case 2, when my minimum element x is the element B. In this case, again, since A and B are distinct and as per the definition of the minimum element, that is said element B is related to the element A and hence A and B are comparable. Okay. So with that, we finish the first part of this tutorial. Thank you.